Hello, welcome back to the WVU Geography 300 video series for geographical data analysis. We are at basically the 1/3 mark within this course. And what we have done thus far is set up the groundwork for the process of inferential statistics, which is the bulk of the course. So, to kind of step back for a moment, we'll revisit and review that general data analysis process we had, and in the context of answering one particular question, I've used it before, of mask mandates and COVID rates. So we start with, at the beginning, we have our general question of interest, what we're kind of interested in. We may start with that question of, are mask mandates effective at reducing the COVID infection rate? There's our general question. Our next step is to collect data. So we go and we find out which places, which counties, let's say, have mandates, which ones do not, and what are the COVID rates for each of those places. So there's our data. Then we would do descriptive statistics. We might do things like find the mean, find the standard deviation of the COVID rates. We might map out where there are and where there are not mandates. We might even go so far as to split the data and do some descriptive statistics of those places with mandates and those without. What is the mean rate of places with a mandate and the mean of the COVID rate of the places without a mandate? So we get our descriptive statistics. We then use that to formulate a particular specific hypothesis. We will then see throughout this, we'll see more detail here on that hypothesis that we'll basically be saying mask mandates, or places with mandates, have similar rates to those without mandates. We would actually set up that hypothesis. The reason for that, we'll see later in this video. Then we would carry out an inferential statistics test. In this case, it would be something called a t-test. I wouldn't expect you to know at this point what test to use for what. You'll see several different statistical tests throughout the next almost 10 weeks, then most of the rest of the course. And at the end, we get our results from, in this case, that t-test, and we take those and we use them to guide policy or to guide some kind of decision making. So a county official might, okay, now that we have the vaccine rolling out, it may be a bit too little too late, but 6 months ago at least, might have looked at something like this to say, yes, I should implement a mask mandate for my community. And use that to come to some decision, because these statistics, they never happen in cultural or social or political isolation. There's always some reason behind why they are being asked. But what we're doing here in this, certainly in this series of lectures, is looking at the process of that step 4, identifying a hypothesis, and step 5, carrying out an inferential test. That process itself can be broken down, those 2 steps can be broken down into 6 smaller steps, basically. So we'll look at those 6 smaller steps here. The first one is to identify those hypotheses. And we're going to split this into two hypotheses, really. One is called the null hypothesis, the other, the alternative hypothesis. No matter what statistical test we are doing, in this inferential statistics paradigm, we're going to be making that split into a null hypothesis and an alternative hypothesis. They are opposites of each other. The null hypothesis is set up where a very generic way of putting it is that there's nothing interesting going on. There's no relationship. So in this specific question, our null hypothesis would be the following. Places with a mask mandate and places without a mask mandate have similar COVID rates. The alternative hypothesis, as I said, it's the opposite. So now instead of they have similar rates, we would say they have different rates. So now we have our two hypotheses. As I said, they are opposite from each other. The next step, once we have our hypothesis, is to figure out what inferential statistical test is best suited to evaluate the likelihood of these hypotheses, particularly the null hypothesis. At this stage of the course, I would not expect you to be able to do that. That will be different at the end. But right now, you haven't seen enough of the different tests to really make an informed decision. So I would just say it's something called a t-test in this particular situation. What the test statistic is going to do is it's going to evaluate the probability the null hypothesis is true, or rather, the probability it is supported by the data. And what we are going to do is to say, okay, I am going to be skeptical, let's say. I'm going to assume there's nothing going on here. I'm going to believe the null hypothesis until I see quite strong evidence that, okay, the null hypothesis is actually not supported by the data. I'm going to flip over to the alternative hypothesis. As I had said, our statistic is going to provide us a probability the null hypothesis is supported. At some threshold, I am going to flip over and say, no, I'm going to go with the alternative instead. Where do we set that threshold? It's actually a very important question in this process. And people frequently don't give it a great deal of thought because there is a cultural norm, and I'll put that here, but it really should be where people give it more thought. Oftentimes, people will use 0.05. P equals 0.05. And say, I'm going to believe and act as if the null hypothesis is true, not until there's a 50-50 chance it flips over to the alternative hypothesis. No, it's P equals 0.05, only a 5% chance. Only then, when the data is quite strong in saying the null hypothesis, no, don't go there. Only then do I flip over. From a legal setting, instead of a preponderance of the evidence, it's beyond a reasonable doubt. What value do you set for your reasonable doubt, though? As I said, many people will just take this 0.05 and go with it without giving it much more thought because that's the most common. Ultimately, that should be guided by what happens if you are wrong. What this is saying is, I'm going to go and say, no, there's the alternative hypothesis. I'm going to take action upon there being some relationship here. What is the consequence of that action if there is actually no relationship? Because this is saying there's a 5% chance the data doesn't support that relationship. With a mask mandate, probably not a great deal of problems where, okay, if you're wrong and masks don't work, you've told them to put something over their mouth for a while. That is not the end of the world. So we might have a higher threshold, 0.1 or even higher, because when implementing a mask mandate, the cost of that being wrong, probably not that high. On the other hand, if there is a major cost, and in the COVID situation, there's probably a bigger cost if you're telling people the vaccine works and it doesn't. So they might have a much stricter threshold. The strictest I have seen used has nothing to do with public health, or geography for that matter. It was particle physics, of announcing, where the physicists were announcing they had found evidence of a new fundamental particle. This is, you might want to say, the physics equivalent of discovering a new continent. This is really big news. It was going to be on every single headline, or the top headline of every science section of newspapers around the world. The consequences of getting that wrong then, really massive consequences, because you've just put something that's a false claim on worldwide news. Well, that's a problem. So they picked a much stricter threshold, 0.00001. So there's only a 1 in 10,000 chance they were wrong when they said this is a new particle that we have confirmed exists. So that choice, as I said, it tends to be about, really should be about, what happens if you get it wrong? The consequences of that vary from situation to situation, and so this should vary accordingly. The next step in this So this now brings in the idea of distributions. We're going to find a distribution of the test statistic, so this T statistic, if the data is going to support the null hypothesis. So it's saying, okay, the data supports the null hypothesis. If that is true, what would we expect the value of t to be? It so happens that the t distribution is a lot like the normal one, just with the slightly shorter middle and slightly fatter tails. Forget this t statistic, t distribution, if I know the null hypothesis is true. Actually finding this distribution, the software will handle this for us. So don't worry about the math involved in that. Our next step is to get the p-value. So this p-value, it relates to the distribution by saying where in that distribution is the data from our, or the value from our data. So I might find t-value of, I just picked something here, 1.89. Now, the way I have set up my hypotheses, they are similar or they are different. Different could be places with mask mandates have a higher rate of COVID, places with mask mandates have a lower rate of COVID. Those are both situations where it's different. The way that is set up then, and we'll see next week how we can change the t-test to accommodate different hypotheses. Where in the distribution is that statistic? Which is then the p-value the proportion that is shaded. Again, I just picked a number. I don't know if this t corresponds with that p-value. Again, the software will handle those calculations for us. So there might be 4.8% of that total distribution shaded. What that means is finding a t-value of 1.89 or more extreme being further away from the middle, further away from 0, and therefore saying, okay, under the null distribution, under the null hypothesis of there is no relationship, I would expect a value of 1.89 or more extreme, whether higher or lower than negative 1.89. A more extreme value would happen less than 5% of the time. Having set that threshold, as I said, at 0.05, I then take the last step Now in this case, the numbers I put down, my p-value was less than my alpha value, which I set out at that decision threshold before at 0.05. So based upon that, I would say the data supports the alternative hypothesis. That alternative being that there is a relationship, that mask mandates do have an effect upon COVID rates. So there is one thing to note, one last caution to note here. In this decision, I'm confirming it based or rejecting it, in this case rejecting it, based upon the data that I have. Recall from some of the earlier weeks of the course that the data have errors. No data is perfect. There could be measurement error. There could be sampling error. There could be, say, people who have COVID but never show up to the hospital to actually get their infection recorded. There could be issues where we might have information that's out of date. I might have collected my mask mandate information on April 1st, but some other place implemented a mandate on April 15th. And would then be out of date. So there are different ways that our data can introduce uncertainty into this process. And we are then again precise in trying to say the p-value is the probability that the null hypothesis is supported by the data, rather than the probability the null hypothesis is true. Because if I say it's not supported by the data, that probably means that that null hypothesis isn't true, but there is always that chance that actually the problem's with the data, that the data was wrong, and because of that, we say it's not supported by the data that we have. That also gives us the option of, well, okay, if I really feel like something went wrong here, I can go and collect more data, rerun it, and then hopefully with more data have more confidence in the results because I am confident that my data is more accurate and better, basically better data. So to recap, we have this process of inferential statistics, starting with developing the null and alternative hypotheses. Then once we have those set up, we pick a test statistic to evaluate the probability the data supports the null hypothesis. Also, we pick a threshold of what likelihood of support we want for the null hypothesis to do this last step of confirming or rejecting the null hypothesis. We make that decision before we run the test, so that we cannot have those results bias our choice of that threshold. Then we find what is the distribution of that test statistic if the null hypothesis is true. Once we have that, the computer handles it for us. Step 5 is we take our actual data and we put it into that distribution to see, is it within the range of that distribution that would be supporting the null hypothesis, or the part of that distribution that supports the alternative hypothesis. And last, based upon which part of that distribution it's in, we would then say, I support the null hypothesis, and I'm going to take action based upon the null hypothesis being the case. Or I'm going to flip and say, no, it's actually the alternative hypothesis. We need to take some kind of action under the premise that the alternative hypothesis is the one that is actually going on here. I recognize this is perhaps quite a bit as a framework to understand, and it's been one of the longer videos certainly. So, as always, if you have questions, if you have concerns, please feel free to raise them by email or in one of our class Zoom sessions. So, thank you for watching. Have a good one. I'll see you at the next video.